Welcome to Benu Networks presentation on energy optimization with a Cloud-Native BNG. We're going to be covering an intro of Benu Networks, the current situation with green initiatives that's happening worldwide, and then we're going to be going through some of the aspects of energy consumption in a BNG, what tools or mechanisms can be used to save power, and how it compares to a commercial router. We will be doing some analysis based on actual testing that we did in our labs. And then we'll conclude with a summary. So very brief intro of Benu Networks. Benu has been around for 12 years. It's a company headquartered in Boston with offices around the globe. We're the industry leader in SD-Edge solutions, and we cover different product types, network functions that are deployed in cloud-native platforms. So we cover BNG, wireless access gateway, CGNAT, AGF, and also SASE solutions. Our products are deployed at scale worldwide in different continents, in the Americas, North America, Europe, Africa, and Asia. Globally, our SD-Edge platform is connecting over 25 million homes and businesses, and about 7 petabytes of data run through our platforms per day. We also work with key partners worldwide, ranging from infrastructure providers such as Intel, or switch vendors such as Ciena, Atran, Arista, but also with software vendors that do provide NFVI or cloud-native platforms such as Red Hat and VMware, as well as Dell as a server vendor. Based on what's going on right now, there's worldwide initiatives actually to move to greener platforms, optimizing power consumption in all the deployments. And we're going to be going how a cloud-native architecture actually helps to reduce power use. So we did this testing in our Benu labs, and the basic premise of this is trying to replicate what happens in a real-world scenario in an operator network. So when we see traffic in those types of networks, we see the bandwidth use varies throughout the day. So every hour, actually every minute, we see traffic ramping up or coming down. And typically when we look at the traffic patterns for different operators, that the traffic line is very similar over a 24-hour period. So the more bandwidth that a network function needs to process, the more throughput. There's going to be more packet processing, and that's going to increase CPU utilization. Potentially the frequency of the cores is going to increase. It's going to draw more heat, and then a higher fan speed. So all of that contributes to higher power consumption. With a cloud-native BNG, there's some architectural advantages which can help actually to mitigate power consumption, or really optimize power consumption in certain hours of the day, versus a monolithic static hardware-based solution that has more of a baseline power consumption, and it's very hard to shrink down or scale out. So we are really comparing a commercial router from a large, well-known vendor with a cloud-native BNG approach. With a commercial router, what happens is that it's usually oversized based on the different hardware options. So you don't find a lot of granularity in the different hardware options. So you always need to go with a higher configuration based on your traffic needs in the peak hour. Whereas in the cloud native solution, really the user planes can be tailored, customized to the actual bandwidth demand in that particular moment in the network. So in a commercial router, it's really hard to scale up or down. The solution is typically done by adding more cards, line cards, or additional chassis. And really the options to limit powers to save power, it's really limited. In the case of the BNG, on a cloud native approach, the user planes can be scaled up and down based on time of the day, and it can also be scaled out to multiple servers, or it can be combined on less number of servers. The Cloud-Native BNG also runs on commercial servers, which allows for additional power saving techniques that Intel provides, allowing, for example, cores to be shut down or run at minimal power, as well as changing or adapting the frequency of the cores in real time based on load and demand. So the traffic pattern that we used is an actual operator a traffic pattern from different research papers, as well as data that Benu gathers from live networks. And we can see that over a 24-hour period, there's a peak hour. In this case, we're considering a peak of 5 megabits per subscriber. And there are going to be valley hours during the night where the traffic drops down to about 1.2 megabits per subscriber, and then it starts ramping up in afternoon and evening. So, we can see here that there's a big difference in bandwidth demand and throughput from those peak hours and the valley hours during the night. So we're going to see what tools and mechanisms we can use to optimize power in this environment. So what we did to test this setup is we took a reference configuration consisting of 40,000 subscribers, and then we figured, okay, at in the peak hour we're going to need 5 megabits per subscriber, so that's 200 gigabits of throughput. Whereas in the lowest hour of the day, we're just going to need a probably 30% or less of that throughput. So we tested this in our lab with leaving the CPs connected. So the idea is that we run with a traffic generator, and subscribers were connected to the network, those 40,000 subscribers. The average bandwidth per subscriber changes throughout the day, so we split the whole day in 24 different hours, and then we also worked on an approach to resize the virtual BNG, scale it up and down based on different time periods. Okay. So we chose to scale up and down the virtual BNG in 3-hour periods. And then we measured the power consumption, the resulting power consumption, and then compared against a flat line of always consuming the same power, and also comparing it with what a commercial router, how much power it would draw. The testing setup consisted of Dell R740 servers, as well as a T-Rex traffic generator in our lab. And what we did is, as I mentioned earlier, we worked in 3-hour intervals and determined what was the number of vCPUs that our user plane would need for each one of those time periods. So the total number of virtual CPUs required ranged from 20 up to 56 vCPUs. The idea is that in the high peak, we're actually utilizing 56 virtual CPUs, or the Kubernetes pod that is running the BNG user plane, it's utilizing those virtual CPUs. Then what we do in the rest, in in the valley hours and the rest of the time periods is modify the pod and reduce the number of resources that it needs from a vCPU and memory perspective. So we do this every 3 hours, and obviously when we are running with 20 vCPUs, there's much lower power consumption than when we're running 56 vCPUs. So we ended up with a model of the total bandwidth versus the power consumed in watts. And this number that you see here, it's for a one-to-one redundant server setup, meaning that we had 2 Dell servers, R740s, running BNG user plane pods at the same time to be able to absorb this traffic. So what you can see is that we had a peak of 780 watts and really a low point of 546 watts. So this was done, as I mentioned, by scaling up and down the user planes, scaling it down during the off-peak hours, and shutting down idle cores during off-peak hours. So in this case, what happens is that active user planes are distributed across the servers and they take the load. It's going to be the same number of subscribers with less bandwidth, therefore, less vCPUs will be required. If we compared this to what a commercial router would look like from a power consumption perspective, running at about 400 gigabits per second and with a typical power use of 850 watts with a max of 1.1 kilowatt, you can see the line, the power line, it really doesn't drop significantly below the baseline. So we're assuming a typical power use of 850 watts. Now, if we compare the virtual BNG cloud-native approach with a commercial router, we can see that there's a significant difference, and the virtual BNG actually draws 58% less power. So in summary, the cloud-native architecture can contribute to global green initiatives and optimizing power in different types of cloud-native and cloud CO deployments. There are multiple techniques that can be used to save power in off-hour and low peak hours. We as Benu are also working very closely with Intel, finding ways to further optimize power in the latest generation Ice Lake architectures. When we look at monolithic hardware-based solutions, they're typically burdened by the base power that's needed when you switch on the chassis and when they're running at zero load. So at low processing or low bandwidth, there isn't a lot of difference between running at low load or actually running 200 or 400 gigabits per second. In the case of the Cloud-Native BNG, we have a lot of flexibility to scale up, scale down based on a time of the day. And Kubernetes offers a great framework to orchestrate pods and bring them up and down and adjust resources as needed. And the conclusion is that a Cloud-Native BNG deployment can actually save up to 60% of power compared to typical commercial routers. Thank you very much.